Welcome Calculus 2 students. We are looking at our last section in Chapter 7, discussing improper integrals. The first up would be infinite integrals, and we're going to be able to integrate where one of our limits of integration is infinity. Now, we might have an answer to this and we might not. If we do have an answer and the limit does exist, we're going to say that this improper integral converges, and if we don't have an answer to our limit, we're going to say it just keeps getting bigger and bigger and it diverges, so we don't have an answer to that. So notice that for this particular function it keeps getting smaller and smaller, so we can say that that limit, or the area under the curve, there is a value to which this this function is approaching. And how we do that is we just replace that that place on the integral where we have either an infinity or a negative infinity with that limit, and that would be by definition. And we could do the same on both ends if we want. So let's look at example 1, where we are computing our limit from 0 to infinity. So I'm going to say that this is the limit as b goes to infinity of the integral of from b to 0 e to the minus 3x dx. I compute this just like I normally would, and at the very end I'll take my limit and see if it exists and get that answer. So this would be e to the minus 3x over negative 3 evaluated from b to 0, plugging in those limits of integration. Alright, this is what I get when I plug in that b minus the 0. I'm going to do a little bit of algebra here and then I'll take that limit. Alright, here's what I get, just rearranging this a little bit, and the first one is 1/3. The first term, I'm just going to use the property where I can just take the limit of each because it is a sum. And then as b goes to infinity, this denominator gets bigger and bigger, and this guy then heads off to 0. So it is 1/3 minus 0, and this answer is then 1/3. For my next one, I'm going to have to look at this one in two separate cases. I'm going to have to look at it from both a to c, taking a limit, and then from c to b taking a limit on the upper end. So I have to do it in two separate stages with that sum. So I'll write that down. Alright, I've written it in two separate cases. Now in integrating this, I find that this is just a straight up inverse tangent, so I'm going to write that down and as my two separate limits, and evaluating at those 2 points. Okay, I have that written down. I need to choose a c. I'm just going to choose 0. Makes it convenient, and you can choose whatever you want, just as long as you put the same value in for your c. Just inverse tangent of 0 is 0, so that makes that nice. Now I'm just going to write down what I have. Okay, and now as a goes to negative infinity, this guy here goes to pi over 2, and same for this next one. As b goes to infinity, this one goes to pi over 2, and we have that this indefinite integral then equals a pi. Alright, next we're supposed to find the values of p for which this integral converges, so I need to find this integral. I'll just go ahead and do this integral part here because that part's pretty straightforward. Limit as b goes to infinity, and this is going to be 1 over 1 minus p is what that would end up being, times, and that would just be x to the 1 minus p. And we would need to evaluate this from b to 1. Alright, so let's write down what we have when we do that. We're going to have the limit as b goes to infinity of, I'm just going to write the x on top, x to oops, not x, this will be b. Alright, just filling in the gaps there and doing from b to 1. This is what I'll end up with, where this guy here is just going to end up being a 1, and then that's provided p can't be 1. So they don't say that, so I'm going to have to go ahead and say that p cannot be equal to 1 in this case. So we'll have the limit as p goes to infinity, and I'll write that down. Alright, we'll look at our different cases now, because this is going to be different depending on what p is. So if p is, let's go ahead and do the greater than 1 first. If p is greater than 1, this b is going to be to a negative exponent, which means he'll be in the denominator. And if he's in the denominator, then this term goes to 0, and all I'm left with is, I'll write down, let me write down. Alright, that would be what I'm left with, because this is the only term with a b in it, so it's the only one that's really going to do much with. And you could say that, then make it pretty, you could say that this was, let's just swap these around, p minus 1. Okay, so it would be a constantless, and so it would at that point converge. Case 2, let's look at it if p is greater than 1. Oh, I already did greater than 1. I mean less than 1. Okay, if it's greater than 1, I mean less than 1, then this is a, this would then just be a b on top, and it would then just get, it would be just some large number. And if, because this value here would just keep getting bigger and bigger, the more negative that it was, which means that that's going to diverge, and we would say that this thing would then go to infinity because it just keeps getting bigger and bigger. Now let's look at this case 3 where p equals 1, and that's not going to be much good either, because if p equals 1, then what we're going to have is, let me write it down. Alright, if p is equal to 1, then we've got this integral here, and then we're just going to say, and that's just of course my natural log, and as this gets bigger and bigger, the natural log gets bigger and bigger, so this also equals infinity, so it also diverges. So the only case where this has a valid answer would be, or a finite answer would be, if p is greater than 1. Nice, they've given us an example where we get to do 3 separate problems for one example. It's lovely, don't you love it when they do that? So I'm going to use the disk method here. Just make this a disk and rotate it. And as you can see there, this is going to be, if I use the disk method, it's pi. It's going to be evaluated from 1 to some infinity of this function squared, so that would be 1 over x squared dx. In order to solve this problem, I will rewrite it as a limit, and then I'll integrate. Alright, this one was pretty straightforward, so I just went on through with it, and I integrated this 1 over x squared and replaced that with my limits of integration, and I ended up with just pi. The next one is surface area, so I'm going to have to remember my surface area formula, so let me go ahead and write down the surface area, and I'll write that down for you. Alright, oh my, so this is what my surface area formula is going to look like. There's just a straight surface area formula, and here's where I plugged in for my particular function. So let me play with it a second. Alright, this is going to be a bit messy to solve, so instead of solving it directly, we'll just say that it is always going to be less than some sort of, if I look at this thing here, because it's 1 plus x to the 4th, this is always going to be, actually I'll make sure that it's always going to be greater than something, because that would make that, if I say this, oops, if I say that's x to the 2nd, because it's pretty close to that, over x to the 3rd, if I took the square root, and if I say that that's always going to be, that thing that I just got is always going to be greater than that, so I'll write it like this, 1 over x cubed. It's always greater than that x squared over. So that's always 1 over x. And I already know that this 1 over x is then going to diverge. I looked at that in a previous problem, so then I'm going to say that this thing just keeps getting bigger and bigger and diverges. Okay, for question C, we're going to use the shell method. We're rotating this about the y-axis, and we'll be integrating them from 1 to infinity using the shell method, and that will mean I've got, hold on, here will be my integral. Well, that makes this one really easy. That makes this thing equal to just 1, so then it's x evaluated from b to 1, and I'll put my b and my 1 in there. Alright, well, when I got this and I put infinity in here, this sucker is just getting bigger and bigger all the time, so this thing is diverging, so I'll say we don't have an answer on that bad boy. Next, we're going to be looking at integrals where the value of our function approaches infinity, and we're just going to extend that definition so that we're not going to infinity or to negative infinity, but the value of our function is doing that. So we're just extending that definition and saying this also equals the limit. So we'll look at one of these. We're to find the area under the curve. So my area is going to be, now I could evaluate this from 3 to negative 3 and break this up into 2 separate limits, but let's just double the silly thing, and let's just say, and just do either side, where we go from 0 to 3 of our square root of 9 minus x squared, and then dx. And then what I'm going to do is look at this limit and say, hey, we're at infinity here, and we're approaching that 3 from the left. So using my definition from above, that's going to look like 2, the limit, and we'll call this c going to 3 from the left of the integral of 0c. That integral, and this is just straight up inverse sine with my a being 3. So let me get this written down. So there we have our inverse sine. Now I'm going to plug in my limits of integration and then take my limit. Notice that when x is 2, this thing is shooting up to infinity or negative infinity because I have a 0 in the denominator. So I will break this integral apart and look at it from 1 to 2 from the left and from 2 from the right to 10, and I will integrate it from here. Alright, I've integrated this, and now I'll plug in my limits of integration, and then I will go to take my limit. Alright, just doing the computation on that. We get 9/2. Alright, if I notice that this hypocycloid is 4 of these arcs, then I can just say that I'm going to take the arc length from 0 to a of just one of them and just multiply that by 4. That means I need to compute the derivative of my f prime, so I will go ahead and get that. Alright, I had to get that f of x, and there he is. It's the top and the bottom. Of course, I'm just looking at one of them, so I'm just going to look at the positive one up here on top. And I'm going to work that from there, so y prime. And then I'll use the chain rule here. Okay, there's my f prime. I'm getting ready to put it in here. I'm kind of excited because this square root gets to disappear when I square it, but I'm not really all that excited. I'll see what I get whenever I'm putting it in there. Okay, I wasn't really excited about this, but now I'm going to distribute, and it looks like that x is going to be to the 0 power, which means that'll be a 1, and I'll have a 1 minus 1, so I'm just going to have this square root of, I'm not sure that I'm necessarily thrilled, but it's just going to be a to the 2/3 x to the negative 2/3, and messing around with that, this a to the 2/3 can come out. He's just a constant, so you're going to get 4a to the 1/3 integral of 0 to a, and then this is just going to be x to the minus 1/3 dx. Oh, now at 0 this thing is going to be shooting up to infinity, so I'm going to have to use my limits, and that's what's the deal here. At first I was thinking, well, there's nothing wrong, but there is. Alright, there's what it looks like with its limits. I'll just integrate this and plug in my limits of integration, then I'll do our limit. Alright, so what happens now is if I take this limit, this thing just goes to 0. So all I have left is this constants, and that's going to work out rather nicely, so I'll write that down. Okay, well, I get 6a. Alright, because got a little cancel in there, and a to 2/3, so either 1/3. It's just a to the first, and I'm good to go there. Let's go on to the next one. Alright, reading through this problem, what I'm going to have to end up doing is finding the ratio of each of these two integrals so that I can find the concentration of a certain drug. They give me each of these C values here, and then I'm sure I'm going to have some, I've got some sort of limit at infinity, and so I'll have to figure out what to do with that. So let me get this first set up. Let's just go ahead and do this AUC naught, and then I'll do AUC initial. Alright, in looking at this integral, I see I'm going to integrate, and I'm still going to get some e to the minus 3t, which means that at infinity this is going to be in the denominator. So I think things are going to drop nicely. I'm going to go ahead and compute this integral and put in my limits of integration. Alright, as b goes to infinity, these are in the denominator, so both of these two components go to 0. And just doing some number crunching, you'll get 264 for that AUC naught. Now we'll compute the AUCI, and then we will just take their ratio. Alright, we get our ratio equal to 0.792, which just means that the oral administration of the drug is about 80% as effective as the IV dosing. And that concludes 7.8.